When we look up to the stars, who among us hasn't wondered if there's anything out there? Are we alone? In 300 BC, Epicurus wrote, "There are infinite worlds, both like and unlike this world of ours. We must believe that in all worlds there are living creatures and plants and other things we see in this world." In the 11th century, Saint Albertus Magnus wrote, "Do there exist many worlds, or is there but a single world? This is one of the most noble and exalted questions in the study of nature." Today, scientists continue to pursue knowledge of and evidence for the existence of life in places other than Earth. That search ranges from the farthest reaches of the universe to the depths of our oceans. Though its existence remains purely hypothetical, there are numerous hypotheses about how and where life might have emerged elsewhere, and whether or not it will resemble what we are familiar with on Earth.
One of the key questions in astrobiology is, as you know, are we alone? Is there extraterrestrial life out there? This is a question I think everybody cares about and wants to know. But it also encompasses another idea, and that's how did life start here on Earth? How did we get here? So both of these topics are included under astrobiology. And just out of curiosity, how many of you had heard about astrobiology before this talk, by show of hands? So quite a few of you. That's good. So the message is getting out there. This is an important field of research that's supported by NASA. So are we alone? Well, we thought we had the answer to that question. If you remember back in 1996, the NASA press conference, it said, we've got life in this meteorite from Mars. We've got evidence for life. And it really set off a firestorm of media coverage. People were going fanatic, basically, about this idea that, Mars contains evidence for life. And what happened is, at this time, I had just graduated my undergraduate degree at San Diego and had no idea what I wanted to do for my research. I was pretty much clueless. But after this announcement, I said, this is it, astrobiology. It had me right at that moment. I said, I got to study meteorites. I got to learn more about chemistry and how we search for life. And so what you saw is basically two camps kind of emerge. You had the red team, which believed that all the evidence in this Mars rock was Martian in origin. And then you had the blue team, which I became part of, where we were more skeptical. We said, no, this is maybe contamination from the Earth. What we have to remember is that this potato-sized meteorite called Allen Hills 84001, which got blasted off the surface of Mars, landed in Antarctica. And it spent about 13,000 years in Antarctica before it was discovered. So there was plenty of time for it to basically absorb contamination from the surrounding environment. Nonetheless, there were some very interesting features of this rock. On the inside, they had these amber-colored carbonate globules that they claimed were basically fossil remnants of life. And inside these carbonates, you could see these little worm-like structures. They said, this is it. This is the fossil of life. And more importantly, they actually found organic compounds associated with these fossils called polycyclic aromatic hydrocarbons, or PAHs, which they claim were basically the degradation products of the life itself. Now, the skeptics, including myself, argued, well, that's nice, you see these worm structures, but you can form these without life, too. We see these in non-biological carbonates, these sort of structures, and more importantly, these are extremely small. So most people felt that you couldn't actually have a microbe be that small, a billionth of a meter in scale, tinier than the thickness of your hair. And the organic evidence was a little bit mixed too. PAHs are really not good biomarkers, okay? They're ubiquitous in space. You see them in the interstellar medium. They're everywhere, not necessarily associated with life. When you barbecue on a Sunday and you overcook your burgers and you form that black stuff, that's PAHs. Okay, this is not really living material, okay? It's cooked. So we were very skeptical. And my research, we looked at the amino acids, which we would argue are much better biomarker. These are the building blocks of our proteins and enzymes that basically allow us to function. And we found that, yes, there were amino acids in this rock, but they looked identical to the Antarctic ice. So we concluded that there was an infiltration of organics from the surrounding environment that really complicated our interpretation. So the life on Mars debate continues today. It's been going on for some time now. I think most people admit that we really need to go to Mars and analyze a sample in situ. We want to get rid of the terrestrial contamination problem. We may have to actually go to Mars and pick up a rock and bring it back here and study it in the laboratory to figure out if there's life. But it really spurred interest in Mars again, which was a good thing. So let's come back to Earth for a second. This is the only place that we know definitively that life exists. Okay, this pale blue dot. The conditions on Earth are really perfect for life. You have a thick atmosphere. You know, we've got that ozone layer, which fortunately shields us from all the harmful UV radiation that can destroy life. We've got abundant liquid water oceans, which is good because life requires liquid water as we know it. And a wonderful magnetic field that also shields us from high energetic radiation. So this place is protected, and we really need to do our best to keep it that way. So what are the requirements for life as we know it? Well, first of all, I mentioned water already. You need to have liquid water. That's one of the fundamental components of life. You need to have an energy source. On Earth, we've got the sunlight that helps drive photosynthesis. So organisms can actually produce oxygen, and plants. Chemical energy can come from volcanic activity in the subsurface. You know, you have these hydrothermal vents at the bottom of the ocean. Organisms can actually use that energy to sustain a community at the bottom of the ocean. And then, of course, you need the major biological elements. Carbon is the most important one. We're built on carbon. We are carbon life forms. But there are several others that are important as well. Hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So these are the kind of elements that we want to look for when we're searching for life elsewhere. Now, when you have all these things together, you have a habitable world, okay? But that doesn't necessarily mean that life evolved there. It just means that place has the potential for life, and whether or not all the neat chemistry happened to give life is to be determined. So let's take a quick look at the origin and evolution of life on Earth. The Earth's really old, 4.5 billion years. The solar system formed about 4.6 billion years ago. The Earth accreted around the sun from this disk. We had a very energetic event that happened at about 4.53 billion years. This is the moon forming impact. So a body the size of Mars crushed into the Earth and basically broke the Earth in two, if you will, and the moon condensed and formed out of that. So certainly we wouldn't expect any life to survive that kind of impact. So the original life had to come later. And in fact, this heavy bombardment period lasted from about the time of formation to about 3.8 billion years ago, where the Earth was constantly bombarded with comets and asteroids and fragments that basically melted the surface of the Earth. You had a lot of volcanism, lava probably on the surface, and again, the conditions at this time would not have been favorable for life. So the oldest evidence we have for life is about 3.5 billion years ago. Okay, we see fossils. So we know the original life had to happen sometime between about 4 and 3.5 billion years. So it had about 500 million years to really get started. And then as you progress down with time, you see more complex organisms. You had the cyanobacteria, which came along, which was great because they started producing oxygen. So you saw a rise in oxygen in the early Earth's atmosphere, which allowed you to form even more complex organisms. So we had cells that actually contained nuclei, the eukaryotes, at about 2 billion years ago. And then eventually you had the multicellular organisms, and then this Cambrian explosion, which nobody really understands the Cambrian explosion, but it was this event where you had this diversity of life just spreading. Many different species at about 500 million years. And then, of course, we're all familiar with the dinosaurs, which roamed the Earth until about 65 million years ago when they were taken out by another large impact called the KT event and extinct. And then, of course, modern humans up till about 200,000 years ago. So we've really only been here a very small amount of time when you look at the entire age of the Earth. So let's take a look at one theory about the original life. And again, I'm looking at that period from about 4 to 3.5 billion years, that 500 million years when we think the first life started. We have this idea of a prebiotic Earth. So you had, once the Earth cooled down from these impacts, you had basically a soup, an ocean soup that contained all these organic compounds, the building blocks of life, the amino acids important in proteins, the sugars and nucleobases, which form basically the backbone in the genetic code of DNA and RNA. So these would have been around in that soup. Eventually, you had this idea of an RNA world or pre-RNA world where these components came together miraculously, and you had some sort of ribonucleic acid. Now, the neat thing is that this nucleic acid could actually split it could cut itself in two and make copies of itself. So now we start talking about evolution and reproduction, if you will, on a chemical scale. So a lot of people think that this is actually the first origin of life, the first chemical that could actually split, make copies of itself, and evolve. And then, of course, as we move along with time, we become more and more complex until we end up with the DNA protein world, which is modern life today. So this is, again, a theory, and there's some actually increasing evidence to support this. We as scientists wish it could be this easy, right? We just make this in a can. You basically shake it up, add some ocean water, and boom, you got it. But it really isn't that easy. This is actually an active area of research, people trying to make the first genetic molecule that can reproduce, if you will, and it's a difficult process, okay? So we certainly don't pretend that we understand how this miraculous event happened. Okay, now one of probably the most fascinating experiments in this field was done by Stanley Miller back in the early 50s, 1953, often called the spark discharge experiment or the Miller-Urey experiment. And what Stanley did in a lab in Chicago was show that if you modeled the early Earth's atmosphere and ocean, so on the bottom left there you see this boiling ocean, if you will, and just like on the Earth where the sun evaporates the water, it condenses into clouds and then rains, he tried to create that cycle, what it might be like on the early Earth. And he used a mixture of gases, including methane, ammonia, water, and nitrogen, and he just subjected them to a spark discharge. So this could be like lightning on the early Earth, for example. And after 7 days, you see kind of a brown tarry goo appearing, and Stanley was kind of taken back. He knew that there was some chemistry happening here, but he didn't know how complex it was. And when he analyzed that liquid, he found 5 amino acids, okay, coming out of that mix. So this was the first experiment that basically demonstrated you can go from non-biology to something that's more biological, at least the building blocks, simply by adding energy, a spark, lightning. So the spark of life is this idea. Okay, now recently in our lab, we actually found some of the original Miller extracts. So these were from 1953 that he had kept stored. Unfortunately, Stanley's no longer living today, but we had cleaned out his lab and found these old vials. And we have state-of-the-art instrumentation now that can really look at this in more detail than ever done before. And we're in fact finding 22 amino acids in this mix. So there was a lot more than Stanley had ever imagined at that time. And keep in mind that there are 20 amino acids in life. So you're making a lot of good stuff here from this experiment. So a really exciting experiment. Now the other theory about how you ended up with this prebiotic soup is that this stuff came from space. And this is an active area of research that I'm looking at right now, analyzing these meteorites. There was a great event that happened in 1969 when a piece of an asteroid landed on the Earth in a village called Murchison, just north of Melbourne. And this meteorite was very unusual in that it had a lot of carbon in it. Okay, so up till this point, they didn't really have one quite like this. So this was a very interesting meteorite. And when they analyzed the organics in there, they found over 70 amino acids in this rock alone. I mean, to me, that's amazing. I mean, most of these aren't even present on the Earth. So they really are extraterrestrial organics being delivered to the Earth from space. And even more recently, even some components of our genetic code have been found in this rock. So this rock it's a treasure trove of information about what the chemistry was like before life. So, of course, one could think about maybe the building blocks of life came from space. Maybe we're all extraterrestrials. So I often get the comment when I'm giving these lectures about, well, carbon's great, but, couldn't there be something else? Why does it have to be carbon-based life? What about silicon-based life, or boron-based life, or ammonia-based life? Something more unusual. Well, indeed, this could be true. Silica is a common element. It's next to carbon in the periodic table, so its behavior, its chemistry is very similar to that of carbon. It can form long chains when combining with oxygen. We're all familiar with silicones there, made out of silica. And it can also, like carbon combines with hydrogen to form methane, a silicon can combine with hydrogen to form silane. So it certainly is an interesting idea. However, in our investigation of samples on the Earth, meteorites, comets, the interstellar medium, space, we find absolutely no evidence of any silicon-based prebiotic chemicals. So at least in our solar neighborhood, it looks like carbon dominates. But, one could imagine something different. For those Trekkie fans here, you might remember Horta in episode 26, and Horta was a silicon-based brain-looking thing. It's kind of bizarre. But Horta survived for about 50,000 years. All of them died out but one, who guarded the eggs, and then they went on to keep going. So anyway, who knows? Now, we may get very lucky in the search for life. This is an icy moon called icy moon of Jupiter called Europa. And of course, we may scan down and see a colony of penguins. That would be great. Proof of life right there. Interestingly enough, today I was looking at the CNN, and there's some British scientists who are trying to spot penguin colonies from satellite, from space. And they actually can't see the penguins because they're hidden in the shadows. And what do they look at? Well, the poop. Basically, the stain on the ice guides them to where these colonies are. So I would argue that really the search for life will probably be chemical. Okay, we're not going to find these moving things that we would, say is life, but we're going to have to look at the chemical fingerprint that life was there. So let's take a look at this idea of a habitable zone. This is the solar system coming out from the sun. You see this blue area, shaded area, called the habitable zone. And really what this is it's a distance from the sun where you're just warm enough to melt ice. Okay, you can have liquid water present. Any closer to the sun, you get too hot, like Mercury or Venus, and you vaporize all water. Not good for life. Any further away, you start to freeze out the water. Again, not really good for life. We need that liquid water to do the chemistry to make life. So Earth, again, fits nicely in this habitable zone. We know life's here. Again, there are some caveats to this. You can't take this literally. For example, we look at our own moon. No life on the moon, but it's in this habitable zone. And then if you also think about the moons of Jupiter and Saturn that have these surface ices and then oceans underneath, well, there may be a possibility for habitability there, but they're outside the habitable zone. So we need to take this idea of a habitable zone with a grain of salt. But it does provide us with a basis when we look for extrasolar planets to look in this habitable zone region for where liquid water would be stable, where we might find life. I mentioned the moon. A lot of you might say, well, we can't do astrobiology on the moon. Why should we go back to the moon? There's no water there. There's no life there. But in fact, the moon actually might be much more interesting than we had thought. They're finding the Lunar Prospector Orbiter in 1999 discovered this hydrogen shown in blue there at the poles. And these are areas of the moon that rarely see light or never see light. They're permanently shadowed. And this hydrogen just may be in the form of water ice. Could have been delivered by a comet, which would be fantastic for astrobiology because now, you don't have to go to a comet. You just go to the moon to understand comets. So that would be really cool. Meteorites could also provide the hydrogen, and even the solar wind can implant hydrogen in the surface. So we really need to go back to the moon and understand where this hydrogen is coming from. LRO will take a step in that direction. The Lunar Reconnaissance Orbiter, which is going to launch here in a couple weeks. Exciting mission. It's going to orbit the moon. It's going to look for water at the poles. It's actually going to even drop a projectile that's going to impact into these craters and kick up a dust plume and then fly through it to sniff for water. So we're all very hopeful that this will provide us some useful information. And certainly with human exploration, the detection of ice at the poles is going to be very important as a resource for exploration. So let's move out a little bit in the solar system to Mars. Is Mars habitable today, or was it in the past? Well, I have to say right now, the surface of Mars is not a place that you'd want to be, okay? Mars has a very thin atmosphere. There's no ozone layer. So all that UV radiation that would just burn you, is getting right through to the surface. So this is not a good place for life, at least on the surface. There's a very weak magnetic field, not enough to shield you from the high energy radiation. But nevertheless, we could think about subsurface life on Mars, potentially. So we can't rule it out. Now, ancient Mars is starting to emerge a very neat story here that ancient Mars was probably habitable. Okay, the picture of Mars now is that there was liquid water a few billion years ago. It certainly had the energy back then. We have to remember the sun was about 30% more luminous than it is today. So that could have provided the energy. Even though Mars is further out, it would have gotten more sunlight, which is good. The key question now is, are there organics? And this is what all the future missions are going there to find out, because if we can find that key, then we have a habitable world. Those are the ingredients. So we're really interested in the possibility of organics. Now, if you recall back into the late 70s, Viking tried this. So NASA actually successfully put and landed 2 spacecraft on the surface of Mars, which is an incredible engineering feat. It basically had an arm that kind of scraped down into the basically top 5 inches or so of regolith. It took that dirt, it put it into ovens, and then heated it up. And the idea here is if there were any organics or life forms in that soil, we'd be able to sniff them out. We'd be able to detect it by mass spectrometry. Well, Viking didn't detect any organics, okay, above the detection limit of the instrument. So people were kind of left scratching their head. We had thought, hey, Mars could have been habitable. Why aren't we seeing it? It turns out that the radiation environment on the surface might be so intense that organics just don't have a chance to survive in the surface soil. So we may have to go deep to actually find these organics. So NASA kind of basically adopted a new Mars exploration strategy. They decided we're not going to go for everything in one boat. We're not going to try to detect life right away. We're going to do a building process. And the key thread here is that water is common to life. It drives climate. It's important in geology, and also is important for human exploration. We need water to survive. So if we ever go to Mars, we need to find the water and understand how to access it. And so really, I like this idea of a stepping stone process. We're going to go to Mars in landing sites that have clear evidence for water, not like Viking, where basically they had no evidence for water at that location, and to really look at the sediments that were formed with water and understand whether or not there are organics present. So this, I think, is going to put us in a much better position than Viking did to address this idea of life and habitability. So yay, okay, Mars was wet. We've got a lot of proof of that now. Rather than just the fancy cartoons that show water, we actually have the ground truth proof of that. Spirit and Opportunity, the Mars exploration rovers, which are still alive. This is amazing, actually. Been going for over 5 years now. These things were designed to last for 3 months. So they're the Energizer bunnies of Mars exploration right now. And they actually uncovered these sedimentary rocks with this layering and ripples that really indicated that these rocks had to be formed by liquid water. So very exciting discovery. More recently, we had the Mars Reconnaissance Orbiter in 2005 basically show us that, yes, there are channels and gullies formed by water on Mars. And even recent gullies, okay? Not billions of years ago, but, hundreds, thousands of years ago. I mean, these things are recent. So water on Mars is happening. It appears to be subsurface, but that's happening. These clays, which are minerals that formed in the presence of water, are also present. This is very important. It's likely that our next landing site for the Mars Science Lab will go to these clays. Clays do a wonderful job on Earth at preserving the record of organic chemistry. So if we can go to Mars and look for organics, we want to go to those clays. And finally, the Phoenix lander, which unfortunately we lost contact with back in March. It wasn't designed to go very long. It landed near the poles, basically froze to death during the winter. But it actually was able, before it died, was able to uncover water ice below the surface. So you can see it there in the white, and then it evaporates away over time. But there is water ice underneath the surface. So this is perhaps one of the most exciting findings about Mars here recently, this detection of methane gas. Okay, Mars is actively burping methane, and we don't know why. I mean, this is something that we need to find out. Where is this methane coming from? I mean, we had thought basically Mars was dead. There's no volcanism, evidence for volcanoes, but no, Mars is alive, okay? It's burping out this methane, and there are basically two possibilities for the source of this methane. One, it could be from biology, could be from life in the subsurface, like methanogens here on Earth. They take CO2 and they make methane. That could be happening on Mars. Astrobiologists would love for that to be the scenario. But it's also possible that geology, volcanism could be releasing this methane. So it could be not associated with life at all. However, I would argue that just the detection of methane is important because that could be an energy source for any subsurface life. So this is really an exciting discovery. Now, the Mars Science Lab is hopefully going to tell us, first of all, what is the abundance of that methane on the surface? Maybe we can find some venting areas possibly, but what is the origin of that methane? Is it biological or is it abiological from geology? This is a huge rover. You see the MER rover there for comparison. And here's kind of a look at the rover family tree. This is at the NASA Jet Propulsion Lab. And you have your little little shoebox-sized Pathfinder Sojourner rover, and then you went up to kind of a golf cart-sized MER, and now, we're up at the Mini Cooper. So hopefully in 2011 we'll be driving a Mini Cooper on the surface of Mars. And just to let you know, this was actually recently given a name, Curiosity. There was a contest, and a young lady won, and so it's now called Curiosity. MSL is huge. It's way too big for airbags. If you'll recall the MER rovers, when they landed, they inflated these airbags, and the thing just kind of bounced on the surface, right? And then when it came to a rest, the airbags deflated, the pedals opened, and the rover drove away. We can't do this with this guy. There's no airbag that we can design that will stop a 2,000-pound rock from hitting the surface. So they have this sky crane idea, which is actually pretty frightening when you look at it. But basically, the thing's going to come down on rockets, and then the rover is going to be lowered to the surface by a tether. Okay, an umbilical cord. That's going to snap. This is going to fly away, and then MSL Curiosity is roaming the surface. So, we've all got our fingers crossed. JPL is extremely talented, and I was told that when they were first pitching the airbag entry, the engineers there were freaking out too. There's no way we can do this, but so they'll do it. Okay, so what will MSL do? It's going to find the carbon. So we've followed the water. We've landed at a site where there was evidence for water. Where are the organics? Where's the carbon? And one of the key instruments here is called SAM, which was mentioned earlier, Sample Analysis at Mars. And again, it's going to pick up dirt. So we're actually going to pick up soils, and we're also going to drill into rocks, collect the powders from the rocks, heat it up to 1,000 degrees in an oven, bake off all the organics and all the other good stuff that's in there, and then we're going to sniff the gas with a mass spectrometer. So we can sniff for methane. We can measure amino acids, the building blocks of life. All of these complex organics will be detected by SAM if they're there. So we're really excited about this instrument. Another cool instrument shown on the left there is called ChemCam. It's a laser spectrometer, basically. It fires a laser beam into a rock and then sparks the rock, basically, melts it, and then it analyzes the light coming from the rock. So from that, you can actually get its elemental chemistry. So if there's carbon in that rock, we can kind of remotely scan for it from a distance. So it's pretty cool. Where is MSL going to go? There are actually 4 sites right now, high priority sites that have been targeted for MSL. And there's been landing site workshops that have been going on now for over a year. And these two I personally kind of like. One is the Eberswalde Delta. And you see here, this is the best evidence for an actual fan. Kind of like the Nile Delta, you have a river and it deposits sediment as you go out. That's it. That's on Mars. So we could potentially go there and, again, look for organics in these deltas. Holden Crater is another cool. This is an impact crater that actually was filled in. So there was a river that broke the edge of the crater on the lower left there and filled up this crater full of water. So it ended up being a crater lake that lasted a long time. And you can see these ancient sediments there that formed as the lake evaporated. Okay, so this would be another good place, in my opinion, to look for evidence of past life. So this is what the program looks like for the next decade. We've got a lot of spacecraft that are currently in orbit. The MER rovers are still going. MSL, we've got our fingers crossed that we're going to launch in 2011 and actually look for organics. And then we've got a series of orbiters. MAVEN is going to launch in 2013, is going to understand the chemistry of the atmosphere, which turns out to be very important for really nailing down your entry, descent, and landing, understanding those parameters. The landing on Mars business is actually still very risky because we don't understand a lot about the winds and the dynamics in the atmosphere. MAVEN's going to help us make that a lot less risky. So that's going to be an important mission. The Mars Science Orbiter in 2016 is going to really do a much better job at sniffing for methane, and it's going to try to locate active venting sites that we might want to send a lander to in the future. The Europeans are also involved with ExoMars in 2016. The neat thing about this rover is it has a drill that can go down about 6 feet into the subsurface and collect sample. So a lot of people feel that we need to drill down to get to the organics. And then the program becomes very uncertain, 2018 and beyond. And I have to say, a lot of this is going to depend on what MSL finds, what ExoMars finds. If these missions find evidence for organics, I have to say that I think there's going to be a big push to actually do a sample return. Bring that sample back. Let's really study it right for life. There's no way we can reproduce what we do in the lab on a rover. We can do a pretty good job, but we might have to bring a sample back to really conclusively nail down the life. Okay, so let's move out even further out in the solar system to the icy moons. I already talked about the penguins on Europa. Well, we don't see the penguins yet, but the interesting thing about Europa is as it spins around Jupiter, okay, Jupiter's tugging on it, and it's kind of slowing down, and it's like slamming on the brakes. You have friction, and that friction causes heat in the interior of Europa, so you're melting that ice. And we think there's a very large ocean in Europa, probably equivalent to the size of our oceans here on Earth. So you can imagine that could be a great place. You could have stuff swimming around in there. Who knows? The key question here will be, how do we get through this thick ice sheet? This thing's several miles thick. This is an engineering nightmare. How do we get through this crust? And there are a lot of creative people out there, so I'm sure we'll figure out a way. Maybe we'll melt something down through it. But we really got to get down under that ice and start exploring that ocean. Well, Enceladus is another icy moon that's really provided us a gift, in my opinion. Okay, we don't need to drill through this ice sheet. This thing is spraying out water. If you look at this is the icy moon of Saturn now, so we've gone further out. You see these tiger stripes shown in blue, and basically we see water ice spewing out the bottom. So this is stuff from the ocean that's coming right out for us to analyze. And the Cassini spacecraft, which is still orbiting Saturn today, occasionally will pass by Enceladus and fly through that ice plume. And it provided some very wonderful data where we showed that there was water vapor, there's methane, there are simple organics and complex organics. Okay, so there's some interesting chemistry here, and I think that we're going to probably in the future see a future mission to Enceladus to look for sort of the building blocks of life, the amino acids and other components that would be life as we know it. One more moon of Saturn I wanted to mention briefly is Titan. Titan's for many years was a mystery because it has this thick organic haze. You can't see through it. We didn't know what the surface really looked like until the Cassini orbiter basically dropped a probe called Huygens there. You see it landed on the surface and provided us the first picture of the surface of Saturn, of Titan. And it's becoming clear now that the surface of Titan, not only you have this rocky methane rock type stuff, but you also have these lakes, ethane lakes, not water, but ethane. This is like, petroleum, natural gas lakes. I mean, bizarre. I guess if you're searching for oil, Titan's the place. If we run out, we may have to go to Titan. But this, it's very cold on this moon. We don't think it's probably too cold for life, minus 290 degrees Fahrenheit. I certainly don't want to be in that situation. But it's a prebiotic chemist's dream. So, the Miller-Urey spark discharge experiment, we have a whole planet that's doing this. And this may have looked very similar to what the Earth looked like in the early stages. So we can learn a lot about, in my opinion, how life formed if we go to Titan and understand that chemistry. Okay, so let's just move out of our solar system and look beyond to other solar systems. As of this morning, I just logged on the website, over 347 planets have been detected orbiting other stars. This is cool. I mean, this means that our solar system is not unique. Okay, these things are out there. Admittedly, most of these planets are Jupiter-sized objects, so they're bigger than what we would really like to find as an Earth-sized planet. So they probably are gas giants, maybe not capable of supporting life, although their moons might be. So it's still very interesting. Fomalhaut b was actually the first direct detection of an extrasolar planet, and this was done by the Hubble Space Telescope. So needless to say, I'm really glad that we had that Hubble servicing mission to keep this telescope going. This thing has really provided us with a wealth of knowledge here. Gliese 581d is what they call a super-Earth, and right now this is the best evidence we have for a habitable world. Okay, it's about 40 times the size of Earth, so not quite Earth size, but it's right at the edge of that habitable zone. Okay, so just at the edge where you could have liquid water stable on the planet. So this thing's 20 light years away, but who knows? Maybe Gliese 581 is capable of supporting life. Now, ultimately, what we really want is to find an Earth-sized planet orbiting another star with liquid water, oxygen, all the good stuff that we have in our atmosphere, and try to identify these things. Well, the Kepler mission is basically doing that right now. It was launched in March of 2009. The way this works is it looks at the star, and as the planet orbits, so imagine that light's a star, as the planet orbits, it blocks the light as it orbits in front of it. It comes around and it blocks the light, and so the light dims. So this telescope is basically looking for that dimming effect as the planet comes in front of it. It's extremely sensitive where it could actually find an Earth-sized planet. So it will measure the size. It'll tell you the distance from that star, which is important because it'll tell you whether or not it's in that habitable zone or not. So very exciting, and it's my feeling here in the next few years we're going to find much more of these Earth-sized planets as well. The James Webb Space Telescope is the next generation Hubble, scheduled for launch in 2014. Extremely powerful telescope, and what this thing's going to do is basically look back almost to the Big Bang, the formation of the universe. It's going to be able to detect the first galaxy that formed after the Big Bang. And so we're going to be able to learn a lot about how planetary systems form from this mission. Okay, so the question everybody wants to know, is there another us out there, right? Is there another intelligent life form? You know, forget the bacteria and all that. We want to know if we can communicate with something out there. Well, Frank Drake actually tried to do that. He developed this equation called the Drake equation, which you may have heard of. It's this complicated thing with all these factors. But basically, n is the probability that you'd have another intelligent life form. So we know from our galaxy, the Milky Way, you have about 10 stars forming per year. Half of those stars roughly have planets. That's a pretty reasonable estimate. What Frank did is he said basically two of these, for each star, two of them are habitable. Okay, well, that you start getting a little fuzzy there, but okay, we'll say at least one. And then he assumes that 100% of those planets will develop life. In my opinion, that's the biggest uncertainty because we just don't know how easy it is to make life. But he assumed that for his equation. Out of that, 1% will be intelligent, which again could be a dolphin or a whale. You know, they're intelligent life forms. And then out of that, 1% will be able to communicate. And by that, he's talking about radio signals. So broadcasting your TV shows, you know, across the ether. And these will be around for about 10,000 years. Well, when you put those together, you get about 10 intelligent civilizations just in our own galaxy. And I think more recent estimates are putting the number closer to 2 to 3. But I don't care. There are over 100 billion galaxies in our observable universe. So you can do the math. I think the idea that we're alone is a little bit crazy, actually. The probabilities just say, you know, we can't be the only one. The question is, can we communicate? Well, SETI is actually doing that actively now. There's the Allen Telescope Array in Hat Creek the Observatory, which actually is being built. A lot of it's already done. And what it does is it combines these radio telescopes. So if you remember the movie Contact at Arecibo, that big dish, that was basically looking for extraterrestrial radio signals. This is going to do an even better job of that. It's going to be able to actually detect an extraterrestrial radio signal 1,000 light years away. That's pretty incredible. I mean, Gliese is 20 light years away, so we already have evidence for habitable planets 20 light years away. So if there's intelligent life there, we should be listening. And we are. And actually, you can do this from home. Just recently, I downloaded a program. If you go to setiathome.ssl.berkeley.edu, you can download a program that will basically help process the data coming from these radio telescopes. So the idea is there's about 3 million people doing this now, and if we can combine the power of all our personal computers at home, we can do a much better job sorting out the signal. So I encourage you to do this. Finally, I just want to thank everybody for their attention, and for more information about astrobiology and astrobiology research at NASA, please go to that website. And there's also a wealth of information outside there, some really good books I encourage you to take a look at. So, have any questions? I guess we got about 15 minutes of questions, so feel free. Yeah, that's a very good question. So the question was, how do we know that the Allen Hills 8401 Martian meteorite came from Mars? And it turns out that Viking, even though it didn't detect life, it did a very good thing, and that it measured the composition of the atmosphere of Mars. We didn't have that information before. So not only did we get the gas composition, it measured the isotopes very accurately. And what they did is in this rock, they basically found these glass inclusions that contain trapped gas inside. They punctured those inclusions, sniffed the gas coming out, and it was a 1-to-1 match with the atmosphere of Mars. So we're very confident that these rocks, and there's a whole suite of these rocks. They're called the SNCs. I think there must be 20 to 30 now that have been identified, rocks from Mars. Allen Hills is the one that's most interesting because it's the oldest. So it would have been on Mars at a time when we think life was there. Yeah, actually, it's funny. I had a slide on Stardust mission. So the question was, what about comets Couldn't comets have delivered the building blocks of life to the Earth? And the answer is yes. And in fact, recently we did get the first known sample from a comet. So the Stardust mission basically had this tennis racket-sized racket that came up, had this material called aerogel, which is a real low-density glass. It's the lowest density material we have, and it flew through the dust. And in this aerogel, we actually were able to trap particles and gases in this sample. This was returned to Earth, and actually our lab participated in some of the analyses of that. And we did find some complex organics that we think are cometary in origin. We found a couple amines and the simplest amino acid, glycine, which is a building block of life. We see that in this comet dust. So that's really exciting. So I think the answer is yes. Not only are you bringing water, but you're bringing in some of the more complex building blocks. Now, is that life in a comet? No, I'm not going to go that far, but it certainly is some of the chemicals you need to get life started. Good question. Yeah, so the question was, what if you go to some of the driest deserts here on Earth? Would you actually find evidence of organic compounds? And the answer is actually yes to that question as well. The Atacama Desert in Chile is actually one of the driest regions of the Earth. Antarctica, there's a desert, that's a frozen desert, is very dry. And we see organics in both of those places. Okay, we can actually detect organic compounds in that soil from the driest region of the Atacama. Admittedly, life has a hard time growing and reproducing in that environment because there's so little water. But it does happen, and we can detect that. And actually, we're using some of those soil samples to actually calibrate our instruments. So we figure if we can detect life in some of the most dry and arid places on Earth, we should be able to do it on Mars as well. Yeah, so the question is, we're basically extremely biased here by our experience in the terrestrial chemistry here. How can we expect to go somewhere else if it's so unusual and be able to identify it? I think that was your question. And I agree with you on that point. I think that the meteorites are telling us a very interesting story because the meteorites basically have preserved that chemistry that took place before life even started here on the Earth. So we're getting a glimpse at that. And places like Titan will also tell us what that chemistry looks like. Now, I admit, in another solar system, somewhere far, far away, maybe you have some other type of chemistry going on. But if I were to hedge my bets, I would hedge it on carbon, at least for right now, because of the meteorite evidence, because of what we see in our solar system. But it's a good question. We have to be open-minded. We can't be so focused on, we got to find that amino acid. No, we got to have techniques that can give us a broad range of compounds. So I agree with you. So basically the question was, have we detected any elements that we don't find here in our solar system? And I believe the answer to that is not yet. I think that, from the light, studying the light from these stars, we're basically seeing things that are similar to what we find in our own solar system from our own star. So I don't believe that they found any unusual element yet. And to be honest, I think that to do that, you would really need to send something there that could make that measurement in situ. Studying the light's great, but it doesn't compare to actually sending something there to measure it right there. Yeah, that's a good point. So the question was that there could be different isotopes, and that's true. And actually, we use the different isotopes as a signature for extraterrestrial form. So the meteorites, for example, have a lot more carbon-13 than carbon-12, as you mentioned. And this basically tells us, boom, this can't be from terrestrial life. This has to be extraterrestrial. Isotopic information is very, very important in these searches. Yeah, so ALH, so the question was, how do the other Mars meteorites besides ALH 8401 tell us about habitability of Mars? And it turns out that, ALH has gotten the most attention because of its age. Most of the other meteorites are not quite that old. They're actually much younger, 1 billion years. So we know that rock was on Mars when there was liquid water on the surface. So first and foremost, that's why it's gotten so much attention. The other ones are interesting as well. There's another one called Nakla. It's a little over 1 billion years old. And right after that ALH announcement, they started working on Nakla. And they claimed to find the same sorts of bacteria, although bigger, in that meteorite. And so there was a lot of attention on that. Oh, Nakla has life too. And again, we studied the amino acids in that, and it looked very different from ALH 8401. We saw very unusual amino acids. And it turned out that those amino acids were identical to the Nile Delta sediment. So the Nakla fell in the Nile Delta, okay? And it basically absorbed all of that contamination, which was very different from the ice. And so I think it told us that contamination's a problem, studying these other meteorites, and we need to be very careful about that. But no evidence for life, I don't think. Well, that's a good question. And I think, so the question was, would the shifting of the habitable zone as the sun dims over time move the habitable zone? The answer is yes. It was likely that the habitable zone was further out when Mars had liquid water, right, and the sun was more luminous. So the question is, could it cool off enough where Venus could eventually be habitable? I would argue probably not. I mean, Venus right now has a really horrible runaway greenhouse effect that just compounds the problem. It gets worse and worse. Venus is extremely hot. I don't see it cooling down fast enough to actually make that a habitable planet. And in the end, we're all going to be fried. I hate to announce this to everybody, but when the sun blows up 5 billion years from now, it's going to cook everything out to Mars. So if we don't get out of here before then, we're toast. So it's going to be the opposite. Yeah, and I want to be a little careful about Venus. When I'm talking about the temperatures, the surface temperatures are extremely hot. People have talked about maybe life forms in the upper atmosphere. We have life floating around on dust grains in our atmosphere. It's much cooler up there, so it could be possible to have some form up there. Yeah, so the question was, what's the atmosphere like of the gas giants, basically Jupiter? It's mainly hydrogen. Okay, they're kind of, in a sense, mini suns, if you will, although they don't have that nuclear fusion in the core that's giving off light. But these gas giants, you have these tremendous winds. The giant red spot on Jupiter, just horrendous winds, 1,000 miles an hour plus. It's crazy. So there's a lot of turbulence in the atmosphere, but we don't think that there's a real rocky surface. And we really want that when we're searching for life like we have on Earth. We've got a continent where you could have life flourish, and you don't have that on Jupiter. And more importantly, you have these really bad radiation belts on Jupiter. So you have radiation that's in the megarads, which is a lot. They basically use this to sterilize beef products. Just cook them to death. Megarads of radiation. So Jupiter's not a good place to be, and some of the other gas giants as well. You really want a rocky planet for life. The food's safe, yeah. If you bring a hamburger to Jupiter, no E. coli. That's true. Yeah. So it's a one-way communication, right? We haven't had radio around that long to be able. They wouldn't hear anything from us at 1,000 light years away, but perhaps they started earlier than us. Maybe they were older, 10,000 years old, and we're seeing some of those ancient radio signals. But I agree with you; it's not going to be a two-way thing unless we get visited. But it's going to be a listening kind of mode. So the question is it conceivable to get a sample from the surface of that icy crust, subsurface? So you're actually talking about getting down into the ocean. Yeah, so this is I think going to be a huge engineering challenge. I think the idea of returning a sample from Europa, it may happen someday, but the first step will just be drilling down or melting something down to make those measurements robotically. It would be wonderful to have some ocean water from Europa. Astrobiologists would go nuts, but I think we're going to have to limit it for now to robotic missions. And we actually have one going there. NASA selected a flagship mission to basically go to the Jupiter-Europa system and send an orbiter around Europa. Now, this mission won't be drilling down into the ice, but it's going to do a very good job at mapping out the surface layer, exactly how thick it is. We don't quite know how thick it is, but if it ends up being 100 miles thick versus a half a mile, that's a big difference. And that's really going to drive our strategy for how we get down there. So it's a good question. So your question is, could we send a nuclear bomb or something to Europa and blow it to smithereens? We've taken that approach with the moon now, right, with L-Cross. It's not a nuclear bomb, but it's a penetrator. And that is another idea. Perhaps if we sent something and blew a hole through the ice crust, it would start spitting out water, ice, and gas and organics, just like we see with Enceladus. That's a possibility. I like the idea of Enceladus because we don't have to bring the nuclear bombs. It's doing that for us right now. So I think we're going to go visit Enceladus again, and I think do a much better job at sniffing out life in that plume. Okay, thank you very much.